Tonight may change everything. An interstellar visitor named C2025N1, dubbed 3 Atlas, sweeps past the Sun in what astronomers call the acid test. If its motion shows added acceleration or energy beyond gravity, someone or something applied force. That outcome would amount to our first credible sign of alien technology. If its motion fits natural models, the mystery deepens but stays natural. Either outcome will force a rewrite of basic assumptions about life, time, and humanity. Over the next days, every precise measurement will carry enormous weight. Stay alert for incoming data. Leave a note with your location and time if you want to follow how this unfolds. Right now 3 Atlas reaches perihelion, the closest point to our star in its passage. Perihelion matters because orbital speed peaks there and small thrusts yield large energy changes. The object arrived from beyond our system with a hyperbolic orbit and excess velocity near 60 km per second. It was discovered on July 1, 2025 by the Atlas Survey Telescope in Chile. Its track shows it will not return. Tonight, at roughly 1.35 to 1.4 astronomical units from the Sun, it passes between Earth and Mars. From Earth observers, the object sits close to the solar disk. Direct imaging during these critical hours remains impossible. The Sun overwhelms faint light. We must therefore watch for indirect clues that reveal whether any non-gravitational forces acted during the hidden hours. Those clues include tiny changes in trajectory, thermal emissions that exceed passive heating, outgassing patterns that do not follow comet physics, and the sudden appearance of secondary objects on independent paths. Perihelion is the optimal moment for deliberate action. An applied impulse there produces maximal change for minimal energy. Engineers know this as the OBTH effect. If the object carries technology or a mission, the physical laws of orbital mechanics offer a natural opportunity to exploit. Observers worldwide will measure positions, spectra, infrared flux, and radio bands. Each dataset will either tighten natural explanations or open the door to engineered origins. The acid test reduces to numbers. Astronomers will search for delta V, a velocity change unexplained by gravity. Our orbital models predict motion with extraordinary precision. A sustained deviation at the millimeter per second level over days will force scrutiny. Natural comets do accelerate through asymmetric outgassing. Those jets produce telltale temporal and directional patterns. An engineered burn would produce a distinct signature in the residuals, a systematic departure from the gravitational model that grows clearer as more points arrive. A delta V of 1 mm per second sits near the detection threshold and might blend with natural noise. A delta V of 1 cm per second or higher would demand immediate, independent confirmation. Measuring such small effects requires top-tier astrometry. Ground telescopes achieve subarcsecond precision under good conditions. Parallax from spacecraft offers orthogonal constraints. Redundancy matters. If separate teams, instruments, and methods reveal the same anomaly, confidence rises sharply. Analysts will plot residuals, tracking how observed positions diverge from the gravitational prediction. A random scatter means measurement noise. A coherent trend means an unmodeled physical force. The hard work lies in separating true signals from false positives caused by modeling errors, star catalog biases, solar radiation pressure, or poorly constrained physical properties like mass and reflectivity. We already hold months of preperihelion data. The object carries the official minor planet center designation and a growing astrometric arc. The orbit shows a dramatic eccentricity near 6.14 and a retrograde inclination around 175 degrees. Those numbers confirm an origin outside our system and a transit that slices through the inner solar plane with surprising alignment to the ecliptic. That alignment stands out statistically. It could be a rare coincidence, a selection bias in our detection capability, or evidence of an intentional trajectory. Hubble observations provided the best imagery before conjunction. Hubble data constrained nuclear size only loosely, with radius estimates spanning orders of magnitude because coma glare hides the solid core. Photometry showed moderate activity consistent with ice sublimation. Nothing screamed engineering at first glance. One measurement stirred debate. Polarimetry of the coma revealed an unusually deep negative polarization branch at small phase angles. Polarization probes dust grain size, shape, and composition. The curve deviates from the textbook Carmateri pattern, hinting at dust properties uncommon in solar system comets. Spectroscopy from instruments like X-Shooter added oddities in relative abundances and line behavior as perihelion approached. Some analyses suggested metal-rich components or atypical refractory phases. Others argued the signals fit rare natural compositions, perhaps material formed in metal-rich protostellar disks or relics from an older galactic population. Aggressive image enhancements circulated online and produced visual rumors of structures. Without the raw, calibrated data and full processing pipelines, those enhancements risk generating artifacts that masquerade as features. Size uncertainty complicates interpretation. A small nucleus means low mass and large response to modest outgassing. A larger core implies much greater mass and a need for stronger forces to explain any measurable delta V. Modelers folded those uncertainties into predictive uncertainty bands. Conjunction widened the window of ignorance. The critical question that follows emergence from behind the Sun: does reacquisition place the object inside the predicted band or outside it? Beyond Earth telescopes, operational spacecraft present windows for follow-up observations. No mission was sent for this object, yet trajectories of probes across the inner solar system create opportunistic vantage points. Mission teams must weigh scientific payoff against operational risk, power budgets, pointing constraints, and scheduled science. The European JUICE mission may have a geometry for observations in the days after perihelion. Venus orbiters or monitors could capture the object as it sweeps near Venus on November 3, 2025 at roughly 97 million kilometers, a distance too large to perturb Venus but useful for trajectory analysis. Earth reaches a favorable geometry around December 19, 2025 when the object sits about 1.8 astronomical units away. That epoch will permit high-quality ground-based spectra and photometry with months of orbital data in hand. Move further out and March 16, 2026 brings a Jupiter window near 54 million kilometers where missions like Juno might supply an uncommon perspective. Each spacecraft observation presents technical and programmatic hurdles. Pointing and thermal safety set hard limits. Data downlink schedules and mission priorities restrict the number of unscheduled tasks controllers will accept. Still, spacecraft located far from Earth could supply parallax and spectral bands unavailable from the ground. The timeline therefore unfolds across months: initial reacquisition within days after perihelion, potential Venus geometry in early November, Earth's best views in December, and a Jupiter perspective the following March. Long-term astrometric monitoring will extend for months and years as residuals sharpen. Observers and journalists should prepare for three broad outcomes. Scenario A, the natural case, finds 3 Atlas behaving like an interstellar comet. Outgassing increases near the Sun, fragmentation or jets follow known patterns, thermal emission matches passive heating, and spectral lines fit plausible astrophysical chemistry. The trajectory may deviate slightly but within models for Carmateri forces. In that case, the object joins the small catalogue of interstellar visitors and supplies new data on planetary system diversity. Scenario B, the engineered case, produces a clean, large anomaly. A delta V beyond reasonable outgassing, a narrow columnated plume inconsistent with solar-driven jets, thermal signatures in locations impossible for passive heating, or release of secondary bodies on targeted trajectories would point strongly toward artificial origin. Chemical lines possibly consistent with industrial processing would compound the puzzle. If confirmed by independent teams, such a result forces immediate coordination among scientific and policy organizations. SETI groups would sweep radio bands. Planetary defense and space situational awareness offices would convene. The global community would face a paradigm shift. Scenario C, the ambiguous middle ground, places evidence on the razor edge. Anomalies appear but remain open to competing natural explanations. Thermal excesses might reflect unusual surface properties. Spectral oddities might indicate uncommon formation environments. Secondary fragments might look like normal fragmentation after careful orbit analysis. Here the scientific community must resist premature narratives. Transparency about uncertainty must guide public messages. Explain what is measured, delineate alternative explanations, and outline the observations needed to choose between them. If a clear engineered signature emerges, the first 24 to 72 hours will run hot. Teams will recheck calibrations, rerun orbit fits with varied assumptions, and seek independent confirmation. The Minor Planet Center, the International Asteroid Warning Network, NASA's Planetary Defense Coordination Office, ESA programs, and specialized astrophysical centers will coordinate data exchange. Media attention will surge. Scientists will answer difficult questions about evidence quality and interpretation while institutions manage reputational risk. If the object behaves naturally, the follow-up effort will shift toward publication, modeling, and proposals for rapid intercept missions for future interstellar visitors. If the record stays ambiguous, debates will intensify and resolve slowly as more data accumulates. The chemical story matters. Spectra carry fingerprints of formation environment. Normal comets show lines from water, carbon monoxide, carbon dioxide, cyanogen, and carbonaceous radicals. 3 Atlas shows some of those features but with unusual relative abundances and unexpected lines. Polarization suggests dust grains with unusual refractive properties or size distributions. Several natural hypotheses address these oddities. One proposes formation in a metal-rich protostellar disk where refractory fractions differ from solar system norms. Another invokes an origin in the galaxy's thick disk, an older stellar population with distinct chemistry. Both fit within known astrophysical processes and preserve natural explanations. A third hypothesis entertains manufactured materials. Some public comments highlighted anomalous nickel features and speculative mentions of volatile organometallic compounds. Peer-reviewed confirmation lacks, so treat those claims skeptically. Industrial chemistry requires controlled temperature, catalysts, and processing absent in wild astrophysical settings. If spectra truly showed refined pure metal signatures without expected oxidation states or mixed phases, natural pathways would struggle to explain the pattern. Bayes' reasoning reminds us that low prior probability for engineered origin demands overwhelmingly strong, reproducible evidence to shift belief. Propulsion hypotheses illustrate what engineered action would look like at perihelion. Chemical rockets would produce hot-directed plumes and ephemeral mid-infrared glow. Solar thermal drives would leave thermal signatures from collectors and directional exhaust. Electromagnetic mass ejection or mass drivers would expel solid projectiles and show electromagnetic pulses and debris streams. Beam-driven pushes imply external transmitters delivering concentrated energy across distance and would leave asymmetric heating patterns. Each architecture has distinct waste heat spectra and plume geometries. Natural outgassing is broad and chaotic and typically points away from the sun. An engineered thruster would be columnated and could point in any direction. Detectable debris from mechanical systems would produce small independent tracks and trajectories inconsistent with simple fragmentation. Energy budgets and mass constraints matter. A delta V of 1 cm per second applied to a kilometer-scale nucleus implies substantial energy but not fantasy. Chemical propellant or concentrated solar power could provide the needed impulse if systems existed. Observationally, the waste heat lies in mid to far infrared bands and spectral signatures might separate active engines from sunlit ice. High-resolution imaging of plume geometry would yield diagnostic evidence. Speculative scenarios extend to seeding campaigns. At perihelion, small releases exploit orbital mechanics to send micropayloads toward planets. A small release velocity near perihelion produces large changes in future orbital energy. A few meters per second could place fragments on encounter paths with Venus within days or with Jupiter months later. Targeting precision varies with required encounter closeness. A cloud of microprobes would be hard to detect at vast distances unless one passes near Earth or a spacecraft. Larger fragments become observable in surveys or through occultations. Detection methods include enhanced photometry, radar returns, occultation monitoring, and repeated wide-area imaging. Spacecraft retargeting for debris searches remains technically possible but costly in mission time and resources. Motives remain unknown. Reconnaissance explains seeding. Depositing relay nodes or science packages fits a civilization aiming to study planetary environments. Seeding with replicating probes enters the realm of profound ethical and scientific consequences. Yet anthropomorphic motives risk misleading inference. Nature might drive signatures that imitate engineered release. Distinguishing human-like intent from unknown natural processes demands careful mechanistic models and exhaustive exclusion of natural explanations. The social and institutional context will shape the narrative as much as physics. Past episodes such as the Oumuamua debate and claimed phosphine in Venus illustrate how initial signals produce intense public interest and professional caution. SETI groups balance the scientific search with reputational risk. Media incentives push for attention while institutions prioritize verification. The Minor Planet Center follows standardized reporting protocols. Informal expert networks trade preliminary results long before public statements. Pressure from social media can force premature responses or stimulate productive follow-up. The system's actors include professional astronomers, observatory operators, mission controllers, planetary defense offices, SETI researchers, and amateur observers whose contributions often prove decisive. Institutions face a trade-off. Rapid disclosure supports transparency but risks false alarms. Delayed announcements reduce error risk but invite speculation about secrecy. History shows repeated false alarms and the slow grind of verification. Fast radio bursts appeared exotic before natural interpretations emerged. The phosphine claim triggered reassessment after reanalysis. SETI false alarms traced to human interference. These cases teach caution. Individual incentives shape behavior. Early discoverers reap professional credit. Institutions guard credibility earned over decades. Media pursues engagement. Commercial actors might prefer hype to attract investment. Government bodies might withhold data for security reasons. Each actor's incentives influence timing and tone of public communication. Prepare a newsroom checklist. Track key data streams, minor planet center residuals, spectral releases from major observatories, infrared thermal data, spacecraft reports, and radio monitoring. Cultivate contacts in planetary defense, ESA, and NASA operations, SETI institutes, and university groups. Frame coverage around provisional findings. Label preliminary data clearly. explain alternative explanations and the observations needed to resolve them. Expect months if not years of follow-up before consensus. The coming days will test scientific rigor and institutional judgment. If 3 Atlas shows no engineered signature, science still benefits through new data on extrasolar materials. If engineered activity appears, humanity faces a profound epistemic and cultural moment. If ambiguity persists, institutions will need measured transparency, careful language, and steady accumulation of evidence. Either way, the story will unfold through incremental measurements, repeated cross-checks, and patient analysis. Watch for the numbers. Watch for independent confirmations. Watch for coherent patterns in residual plots, thermal spectra, and debris tracks. Those patterns will decide whether the night changes everything or whether the cosmos continues to teach us through rare, natural visitors. Each new dataset refines the picture. Observatory networks feed nightly position updates into global databases, adjusting orbital fits by fractions of an arcsecond. Small shifts that appear trivial on paper carry enormous implications when traced over millions of kilometers. Analysts in Chile, Hawaii, South Africa, and the Canary Islands compare residuals through shared software, searching for persistent deviation. Software plots update hourly. Most points line up neatly along predicted curves, yet each deviation fuels speculation. On scientific message boards, graduate students debate whether a faint excess in infrared flux near the tail is an artifact or the first hint of directed energy release. The difference between noise and evidence becomes almost philosophical, defined less by the data itself and more by how much risk researchers accept when interpreting it. Behind closed doors, institutions weigh communication strategies. The Minor Planet Center has protocols for issuing circulars, but nothing in its charter prepares it for potential detection of non-natural acceleration. NASA's Planetary Defense Office tracks potential impact hazards, not alien craft. SETI organizations monitor electromagnetic spectra for signals but rarely analyze orbital mechanics. Coordination between these entities, each with its own culture and constraints, proceeds cautiously. Draft statements circulate internally, laden with qualifiers like preliminary, tentative, and under review. Meanwhile, public anticipation climbs beyond containment. Across social platforms, images, some genuine, many not, spread rapidly. Amateur astronomers enhance telescope photos, overlay orbits, and annotate faint streaks of light with arrows and theories. Hashtags trend. News outlets request expert commentary faster than experts can check data. Popular Science hosts live streams, dissecting every update, interpreting silence as secrecy and delay as confirmation. Scientists find themselves forced into public roles they never trained for, mediating between rigorous caution and the crowd's thirst for revelation. Within research groups, debates turn personal. One postdoctoral researcher, convinced that thermal anomalies in early infrared data represent controlled propulsion, prepares a paper arguing for active maneuvering. Her advisor warns against it, fearing reputational damage if the anomaly fades after more precise calibration. Another group insists the object's orbital plane alignment with the ecliptic cannot be coincidence, while others cite detection bias. We notice objects easiest when they follow familiar paths. Every claim splits into subclaims, every interpretation spawns rebuttals, and every dataset invites fresh modeling. The culture of cautious consensus that normally governs astronomy feels stretched to breaking. Meanwhile, observatories race to reacquire the object as it emerges from solar glare. The first faint detections arrive from the southern hemisphere, low on the horizon at dawn. Each new point feeds into orbital solvers that update trajectory models in near real time. Early fits show no dramatic change, yet the precision is still too low for firm conclusions. Within hours, higher quality data from larger telescopes reduce uncertainties. A slight but measurable offset appears, a few hundred kilometers over predicted position. Statistically small, but enough to start whispers. Could this be the signal everyone was waiting for? Analysts urge patience. A single offset means nothing until trends emerge. As the days pass, instruments across the spectrum engage. Infrared telescopes search for heat spikes. Spectrographs analyze reflected light for compositional shifts. Radio dishes listen in quiet bands where natural emissions seldom occur. Each discipline contributes a fragment of the puzzle. No single observation can prove or disprove technology. Proof, if it ever comes, must arise from consistent patterns across independent methods. Then comes a subtle report. An observatory in Japan detects a transient thermal increase near the predicted nucleus location, lasting less than an hour. The signal is faint and could result from calibration drift, but it appears at the same moment another telescope registers a brightness change. The coincidences spark late-night conferences. Scientists share raw data privately before public release, double-checking timestamps, reprocessing frames, ruling out atmospheric distortion. Days later, independent reanalysis downgrades the signal to inconclusive. The anomaly shrinks back into noise. Relief mingles with disappointment. The system has passed another test of restraint. While instruments measure, philosophers and social scientists observe the observers. The situation serves as a case study in collective epistemology, how modern civilization confronts potentially paradigm-shifting information under conditions of uncertainty. Academic papers on the sociology of discovery begin drafting even before the discovery itself is confirmed. Governments monitor public sentiment, anticipating that even an ambiguous hint of alien technology could destabilize beliefs, economies, and politics. Intelligence agencies quietly examine communication patterns for signs of panic or disinformation campaigns exploiting the event. The object continues outward, its trajectory bending around the Sun and heading back toward interstellar space. By early November, it approaches the plane of Venus's orbit. Venus orbiters execute planned imaging sequences, hoping to capture the faint glint of sunlight off its tail. Data arrives slowly through scheduled downlinks. Engineers compress images, scientists calibrate them, and days later the first results reach Earth. The object appears exactly where gravity predicted. No detectable fragments, no excess luminosity. The Venus window closes without drama. Attention shifts toward December, when Earth reaches the best observational geometry. December brings clarity. Ground telescopes now track 3 Atlas easily against darker skies. Photometry shows steady fading as distance increases. Spectra reveal the same unusual chemical ratios as before but no new emissions. Infrared instruments report declining temperature consistent with cooling debris. Astrometric fits converge. The object's path aligns with predictions to within a few kilometers. The hoped-for deviation dissolves. For many scientists, this ends the story. 3 Atlas behaves like a natural interstellar comet after all. Papers will follow, refining models of volatile distribution in extrasolar bodies and expanding the statistical sample of interstellar visitors from 2 to 3. Yet not everyone accepts closure. A minority of researchers insist that transient deviations during perihelion remain unexplained due to the observational gap caused by solar conjunction. Without continuous monitoring, no one can prove what did or didn't happen during those hidden hours. In that gap, speculation survives. Online communities evolve into quasi-investigative networks, parsing every released dataset for overlooked clues. Conspiracy narratives flourish, claiming suppressed information or classified observations from military satellites. Institutions issue statements affirming data transparency, but the statements convince only those already inclined to trust. Inside scientific circles, attention turns to what the event revealed about process more than about the object itself. The collaboration between global observatories functioned efficiently, but coordination with public communication lagged. Calls grow for a standardized protocol governing potential detection of artificial phenomena, a framework that balances transparency with verification, minimizes speculation, and provides clear thresholds for announcements. Committees form to draft guidelines, blending lessons from planetary defense, SETI, and crisis communication. The legacy of 3 Atlas may not lie in proving or disproving alien technology, but in forcing humanity to design better ways to handle extraordinary uncertainty. In the months following perihelion, 3 Atlas recedes into the outer solar system. By March 2026 it nears Jupiter's orbit. Juno captures a distant sequence of images, faint points barely distinguishable from background stars. Analysis shows no anomalies. The object departs toward the darkness between stars, fading beyond reach. Its hyperbolic path ensures it will never return. In a few years it will disappear entirely from observational catalogues, joining the long list of transient visitors that brushed past our Sun and moved on. When historians revisit this episode, they may see less a story about aliens than a study in collective behavior under the pressure of possibility. The excitement surrounding 3 Atlas exposed how science, media, and public imagination interact in the information age. Data took hours to process, speculation took seconds to spread. The ratio between evidence and interpretation inverted. Each minor update carried social consequences far beyond its technical significance. The object became a mirror reflecting human hopes, fears, and the structure of our knowledge systems. In retrospect, perhaps that was inevitable. Every civilization eventually confronts the question of whether it is alone. For hours, that question arrived disguised as a comet. Whether natural or engineered, 3 Atlas forced humanity to look outward with renewed intensity, to refine instruments, to coordinate across borders, to test the boundaries of skepticism and belief. Even in absence of proof, it expanded the perimeter of inquiry. The final reports list it as a natural interstellar object with anomalous but explainable properties. Yet the narrative will linger, whispers of missed data, hints of deliberate design, arguments that the absence of evidence during conjunction cannot be taken as evidence of absence. Long after the last photon reflected from its surface fades into interstellar night, the debate will continue in laboratories, online forums, and quiet conversations among astronomers watching the next bright dot approach from the void. In the end, 3 Atlas may serve as both lesson and warning. The lesson: how to maintain intellectual discipline in the face of cosmic temptation. The warning: how fragile consensus becomes when mystery meets mass communication. The object traveled tens of trillions of kilometers to graze our Sun once before vanishing forever, leaving behind only data, theories, and a story about how humanity responded when the unknown passed close enough to touch. As the months pass, the excitement fades into routine. Observatory logs close their entries, and datasets are archived in repositories few will open again. Yet the echoes remain. Students entering astronomy programs cite 3 Atlas as the moment they decided to study space. Online archives preserve live streams where millions watched simulated trajectories, waiting for proof that never came. For them, the silence that followed became its own kind of revelation, evidence not of technology, but of scale. A reminder that the cosmos runs on patience measured in light years, not news cycles. Research papers continue trickling into journals through 2026. Each one refines a small piece of the puzzle. One group models the thermal evolution of volatile ices exposed to sunlight at high velocity. Another examines polarization data, proposing new dust grain geometries to explain the negative branch anomaly. A third investigates whether detection bias favors objects aligned with the ecliptic, suggesting that what seemed statistically improbable may simply reflect observational geometry. Each publication narrows the mystery without extinguishing it. The consensus hardens. 3 Atlas was natural, but not ordinary. In conference halls, the object becomes shorthand for the limits of current technology. Presenters speak of the Atlas gap, the period during solar conjunction when observation becomes impossible. Proposals for solar proximal observation platforms multiply. Engineers design concepts for autonomous satellites stationed off the ecliptic, able to track future interstellar visitors continuously. Agencies consider budgets. Private companies sense opportunity. For them, the event demonstrates both scientific and commercial potential, proof that fast, reactive observation infrastructure could serve not only science but defense, resource monitoring, and deep space navigation. The visitors passing reshapes priorities in subtle but lasting ways. Philosophers and cultural theorists take their turn. Essays appear in journals of science studies, arguing that the Atlas episode marks a turning point in humanity's epistemic culture. Never before had so many people followed real-time scientific uncertainty with such intensity. The boundary between expert and audience blurred. Viewers did not merely consume results, they participated in the process of not knowing. Some writers frame it as democratization of discovery. Others call it spectacle, a collective ritual of curiosity turned entertainment. Both readings hold truth. Within SETI circles, debates grow sharper. Advocates for technosignature research argue that 3 Atlas exposed a blind spot, the assumption that alien technology must broadcast signals. What if the most detectable artifacts are passive objects, ancient, derelict, or subtle, passing unnoticed among comets and asteroids? Funding proposals for new search programs multiply, focused on spectral anomalies, non-gravitational accelerations, and thermal outliers among minor bodies. A new subfield takes shape: interstellar archaeology. Its premise is simple: before looking for voices, look for debris. The political world reacts in quieter tones. Parliamentary committees request briefings on potential extraterrestrial material, but the responses are procedural. No evidence of artificial origin, no impact threat, no policy action required. Still, classified briefings circulate within defense agencies, summarizing public and internal data. The notion of technological non-detection becomes an analytic term, a recognition that even a null result can influence strategy. Agencies begin funding small programs to assess how to handle information flow if future discoveries prove less ambiguous. By late 2026, 3 Atlas has faded below detection thresholds. Its coordinates pass from daily bulletins to annual catalogs, then vanish entirely. Yet on the anniversary of perihelion, online communities resurrect the story. Live streams replay archived footage. Comment sections revisit old arguments. Amateur astronomers post commemorative images and note that since Atlas, no new interstellar object has generated comparable attention. The narrative transforms into folklore, half memory, half myth. For many, the absence of final proof becomes the essence of its appeal. Ambiguity sustains fascination longer than certainty. In laboratories, work continues quietly. Samples from comet missions within our solar system offer comparative data. Isotopic ratios, dust morphology, and organic compounds provide a baseline for what normal looks like. As that baseline sharpens, scientists revisit the Atlas spectra with improved models. Some anomalies fade away under better calibration, others persist but shrink in magnitude. A small subset of lines remains unexplained. They sit at the edge of detectability, too weak to confirm, too consistent to dismiss. Researchers mark them as unresolved, promising to revisit when technology advances. Years later, As new telescopes come online with higher sensitivity, the search for interstellar objects accelerates. Detection algorithms run continuously, scanning petabytes of sky survey data. Each new object triggers an automatic assessment: trajectory, brightness curve, spectral type. Atlas becomes the reference model for how to respond, how to balance urgency with verification, curiosity with caution. Protocols once drafted in reaction now form part of standard operating procedure. The memory of overexcitement lingers as a quiet discipline in every subsequent campaign. Sociologists of science begin tracing the event's afterlife. They note how belief communities formed around a single astronomical object and persisted long after empirical closure. Some forums evolved into citizen science groups, crowdsourcing data analysis for future discoveries. Others hardened into conspiratorial enclaves convinced that the truth about Atlas remains hidden. The split mirrors broader patterns in information ecosystems. Transparency breeds trust for some, suspicion for others. The same data, open to all, fuels both understanding and doubt. Decades pass. The generation that watched the livestream grows older. The footage acquires historical weight: grainy screens, scrolling comments, the quiet voice of an astronomer narrating what might be the moment humanity met another intelligence and found only itself. In university courses, the episode appears in syllabi alongside the discovery of Oumuamua and Borisov. Students analyze not only the data but the human behavior surrounding it. The event becomes a case study in scientific humility: how knowledge expands not by confirming our expectations but by confronting their limits. A final irony emerges. Future interstellar detections, far more numerous thanks to advanced survey systems, confirm the diversity of compositions and trajectories once considered anomalies. Negative polarization, unusual chemical ratios, and ecliptic alignments turn out to be common in certain classes of interstellar comets. What once hinted at technology now defines a new branch of natural astrophysics. The extraordinary becomes ordinary through repetition. 3 Atlas, once an icon of mystery, transforms into a calibration point, the prototype for a whole category of phenomena. Still, within the scientific record, the language of those early papers remains cautious and poetic. Phrases like unexplained excess, non-gravitational deviation, and potential artificial analog linger as relics of uncertainty. Reading them decades later, one senses the tension between rigor and wonder, the awareness that for a brief moment, data and imagination stood level. The numbers were finite, the possibilities infinite. And somewhere far beyond the heliopause, the object itself continues its silent journey. It travels through the cold between stars, carrying within its frozen matrix the isotopic signatures that once stirred so much speculation. It does not know we debated its nature, nor that we built stories around its silence. It moves according to physics alone, indifferent to our interpretations. Yet in that indifference lies meaning. Because by measuring, questioning, and imagining, humanity revealed something about itself: the urge to seek significance even in what refuses to speak. In the end, perhaps that is the true legacy of 3 Atlas. Not confirmation or denial, but calibration of our instruments, our institutions, and our imagination. The object passed, the question remained. Each new telescope pointed toward the darkness carries a trace of its lesson, that the universe offers mysteries not to satisfy belief, but to sustain curiosity. Whether alone or not, we learned to look harder, to measure better, to think slower. And in doing so, we came closer not to other minds, but to understanding our own.